I invoke Swami's blessings, love, and grace. I have the privilege to introduce to the audience our distinguished guest, Professor Vadapalli Chandrasekhar. Professor Chandrasekhar obtained his MSc from Osmania University, Hyderabad, India in 1977. He received his PhD degree in 1982 from the Indian Institute of Science, Bangalore, under the supervision of Professor S.S. Krishnamurthy. He worked as a postdoctoral research associate with Professor R.R. Holmes at the University of Massachusetts, Amherst, USA, between 1983 and 1986, and then as a senior research officer in the Indian Petrochemicals Corporation at Vadodara for a year. He then joined the Department of Chemistry at the Indian Institute of Technology, Kanpur in 1987, where he has been a full professor since 1995. He served at the head of the Department of Chemistry, IIT Kanpur, between 2008 and 10, and a Dean of Faculty Affairs, IIT Kanpur, between 2011 and 12. He also worked at the Tata Institute of Fundamental Research, Center for Interdisciplinary Sciences, Hyderabad, as a senior professor, dean, between 2012 and 14, and also as the director of National Institute of Science Education and Research, NISA, Bhubaneswar, India, between 2014 and 17. Currently, he is the Center Director of the Tata Institute of Fundamental Research, Hyderabad. His research interests are in the area of molecular materials, inorganic rings and polymers, main group organometallic chemistry, and polynuclear metal assemblies. He has been a recipient of several national and international awards, including the Shanti Swarup Bhatnagar Award of the Council and Scientific Industrial Research India and the Friedrich Wilhelm Bessel Research Award of the Alexander von Humboldt Foundation, Germany. He is an elected fellow of the Indian Academy of Sciences, Bangalore, and the National Academy of Sciences, Allahabad, the Indian National Science Academy, New Delhi, and the World Academy of Sciences, Trieste, Italy. He has been on the editorial board of several journals, including Organometallics. Currently, he is on the editorial board of Dalton Transactions as its associate editor. His research work is documented in 360 plus publications. May I request our distinguished chief guest to deliver his keynote address.
Sairam, thank you, and it's very nice to be on this conference on recent advances in chemical sciences. So before I start, my pranams at Bhagwan's lotus feet, and I seek his blessings for this talk and for all our endeavors. Before I would like to acknowledge, I would, I would like to acknowledge various. I would like to acknowledge the various organizations, the Department of Science and Technology, and the various people who have collaborated with me, Professor Colesio, Professor Clerac, Professor Jean-Pascal Sutter, Fabrice Poinchila, Dr. Rajaraman, and various students who have been involved in this work. So this talk is based on some of the work that we've been carrying out. This talk is going to be on single molecule magnets, which are compounds of exchange coupled clusters of paramagnetic metal ions. So these are molecular complexes where the transition metal ion or a lanthanide metal ion is encapsulated by an organic ligand. And these molecules, when you put them in a magnetic field, they retain their spin orientation even after switching off the magnetic field. So that is the important aspect in terms of at what temperature they retain their magnetization and how to ensure that this is retained for a very long time. And importantly, no intermolecular interaction is necessary for this phenomenon to occur. In fact, great lengths in terms of design is made to ensure that intermolecular interactions are prevented so that the entire magnetic response is obtained only from the molecule. Different types of single molecule magnets exist. This is a broad family. So the among the various types of compounds that are present are, for example, the first of them is a manganese, large manganese ensemble containing 12 manganese ions, which are bridged to each other by oxide ligands. So this is a molecule where containing different large number of metal ions. You could have a chain like in a coordination polymer where you could have nickel 2 and manganese 3, for example, which are linked to each other by again bridged by different ligands. So in this particular case, so you have ligands that ensure that nickel 2 and manganese 3 have an electronic communication between them. Or in fact, you could just have one metal ion, like in this example where you have this ion which is encapsulated by an organic ligand. So any one of these systems where you have multiple metal ions or a chain of metal ions or just one particular metal ion can function provided we know what to do. So among the first examples is this manganese 12 compound, which has two different types of manganese sites. You have a manganese plus 4 and a manganese plus 3. The manganese plus 4 is in the central location and the manganese plus 3 is in the periphery. The manganese plus 4 sites are among themselves ferromagnetically interacting. And the manganese plus 3 sites are also interacting ferromagnetically. Between them, their interaction is antiferromagnetic. So as a result of these interactions, the spin ground state is 10, and this gives rise to this phenomenon which was realized that if you have a large spin ground state accompanied by a magnetic anisotropy, then you can in fact harness this property. So as I was mentioning, the central cube which is present in this molecule is a cube containing manganese 4 plus ions, and it is surrounded by a ring of manganese 3 plus ions, and this combination generates this particular property. So there is ferromagnetic interaction between the set of manganese 4, there is ferromagnetic interaction between the set of manganese 3, and the two sets couple with each other antiferromagnetic. Okay. Now, as a result of several such studies done over the last perhaps a decade and a half, what is now realized is that the requirements for an SMM, for a synthetic chemist to target this, is that the electronic ground state should be bistable. There should be a large ground state spin, as I showed you, and there should be a uniaxial magnetoanisotropy, which is of the Ising type, that is, for example, preferably, let us say, the direction, and this gives rise to an energy barrier between the possible spin states. And this energy barrier, of course, then prevents a randomization or an equilibrium being reached. If the barrier is large enough, then the spins would stay put in one of the states. However, there are caveats that actually allow this ideal situation to be completely sort of obliterated by relaxation. And this can occur by quantum tunneling, which can, in fact, even at the ground states, even though there is a barrier, there can be an under barrier tunneling, which will result in equilibration. So this is, for example, shown over here. So when we start, let us say the spins are in the lowest spin states, either minus S or plus S state. You put the field on, then one of them is populated preferentially. And when you switch off the field, they're still populated. So ideally, if they have to only cross the barrier and before equilibration occurs, then you can make the barrier as high as possible and ensure that these spins are in the lowest possible state. However, because of various possibilities, these spins can readily go on to the other states that are there on the other side of the hill, and therefore fast relaxation occurs. So the whole process is how to prevent such relaxations and retain the magnetization in one of these wells. Given this, what are the possible candidates for single molecule magnets? So as I mentioned already, the first candidate that was actually looked at and from whose inspiration this entire field was born is this manganese 12 complex. So the idea was that if you can have a large number of transition metal ions put together in a molecule, which are paramagnetic and which can interact with each other so that a large magnetic movement can be realized. And if there is a magneto-anisotropy in such complexes, you possibly have a candidate for a molecular magnet. Additionally, you could also have a possibility where you can utilize two different types of metal ions. You could have a transition metal ion and a lanthanide. Both of them are put together in a complex, and they can interact with each other, generating this property. Alternately, you also can have just lanthanide ions in a complex, and this also can give rise to this property. In fact, all of these have been studied in great detail, and although my talk would focus on lanthanide ions, I will also allude to the other types of complexes. So in all of this, one takes the advantage of this very powerful technique of coordination chemistry, which is more than 100 years old. And in fact, the Nobel Prize for coordination chemistry was as early as 1913 to Alfred Werner. But this technique still remains very, very active and alive, and can be utilized with great success for molecular materials. So what you're doing is you're designing ligands, interacting with metal precursors, and generating various molecular ensembles. Depending upon your design, you can utilize them for various purposes. So the way one can proceed in this area is, one, you do not know really what type of compound you want. You simply know that perhaps if I make a large cluster, that would be useful, but you really don't know how large the cluster should be, or in fact, how do you make them? So one of the ways you can do it is by this technique called serendipity. That is, you're realizing that since you really don't know what you want, but you simply have a hunch that if I have a large enough cluster, it should work, you are preparing a ligand that is multifunctional, and your metal and the ligand are interacting in such a manner that they leave unsaturation in terms of proliferation, and therefore you are likely to end up with a large cluster. The disadvantage of this method is, of course, that you don't know what the structure of the product is, and therefore, in fact, you probably have very little idea about what you're going to get, except that something interesting may happen. The advantage is that oftentimes the structure of the product is something that you would not have been able to design on pen and paper, and therefore you are just allowing nature to come up with a full sort of array of the nature's power and give you structures that you would not have thought about, and then analyze them at leisure. So several such compounds, for example, have been prepared. In fact, the first compound which I talked about, the manganese 12, itself has been realized by such a method. So which was prepared by manganese acetate and acetic acid and potassium permanganate. Clearly, they had absolutely no idea that you were going to get a manganese 12 compound, but this is what they obtained, and which actually opened up the field of single molecule magnetism. And in fact, even in our research unrelated to this field, where we've been working on multifunctional ligands, we've encountered such types of very interesting results. As you can see here, a copper 26, lipophilic copper 26 complex soluble in organic solvents, bridged together by a phosphonate ligand. And in fact, several lanthanide macrocycles that we could prepare by utilizing similar technique. But in all of this, we just did not have an idea that this was the compound that we are going to generate. It was only after the reaction was concluded and the reaction was worked up that we were able to isolate such products. And all of this was accomplished by using polyfunctional ligands. So essentially, the feature of the ligand is they had multiple coordination sites. They had features like, for example, ketoenol tautomerism, as present over here. There is a flexibility of the ligand by, for example, rotation around this NN bond, and so on. And there are points like this phenolic unit, which can bridge different metal centers. On the other hand, while this method of utilizing these polyfunctional ligands is very good and can give you compounds which you could not have perhaps anticipated or even designed, it suffers from the drawback that you can't test a hypothesis. Let us say you want to test a hypothesis that if I want to have a cobalt and let us say a terbium in a complex, and they are separated or they are bridged by an oxide ligand, what would be the property? So this is something that you can't test by the serendipity based method. But on the other hand, you can do this by a technique which is the design synthesis. So here you are designing a ligand which is specifically interacting with a metal ion and specifically giving you a compound whose structure can be predicted a priori. The disadvantage is, of course, that you are limited by your imagination and you're not using the full potential of the nature. But the advantage is you can make a compound whose design is predictable and you can test various hypotheses. So with this sort of a background, we started to look at various ligands, which could be called as compartmental ligands, where we have different compartments that can encapsulate different metal ions. So for our purpose, let us say we have a compartment that can specifically bind to a transition metal ion, and another compartment that can bind specifically to a lanthanide metal ion, and then see what happens. And since we know clearly what is happening, it is possible to systematically do this particular study and engage in this study and get to know what's happening. So we looked at phosphorus ligand, and this phosphorus ligand has different coordination sites. But in spite of the fact that it's polyfunctional, it is really specific. The inner pocket is specific to transition metal, and the outer pocket is specific to lanthanides. So, which is, for example, has this methoxy donor, which is not a very good donor for a transition metal, but a very good donor for lanthanide. So, using such a concept, we're able to prepare compounds which contained in the center a lanthanide, and on either side of it, transition metal. And the connection between the transition metal and the lanthanide is through these oxide bridges or the phenolate. So we know that this is specifically prepared, like custom ordered, if you want to say, prepared in this particular manner by use of this ligand. And then we can study the property, knowing that the lanthanide and the transition metal are bound to each other, bridged to each other by this oxide ligand. And of course, we can, after all the analytical studies, including structure solution by crystallography, which tells you what the structure is, like this gadolinium has an icosahedral geometry around it. The cobalt has a distorted octahedral geometry around it. And the connection between them is through phenolates. We can study them. And we found out that these are excellent single molecule magnets. So once we knew this particular technique of doing this, we of course applied it to various other scaffolds. So here are examples where we utilized it on a ferrocene scaffold. Again, building a compartmental ligand, which is got one compartment that is specific for transition metal, another compartment specific for lanthanide, and we could prepare several such compounds. Where we had here in this example that I'm showing you, you had nickel and lanthanide connected to each other by the phenolates and also connected to each other by the acetate. Now, with this sort of a background, let me just take you to much more recent work, where we use this technique of preparing a compound where the entire magnetism is going to come through only one metal ion, namely in this case cobalt 2, because yttrium 3 is a diamagnetic species and won't contribute to the magnetism. So the synthetic technique is very similar. You have one pocket which is specific to transition metal, the other pocket specific to the lanthanide metal ion, and by utilizing this sequential sort of protocol of addition, you can specifically generate compounds in almost quantitative yields where you have cobalt and yttrium located in this manner and connected to each other by the phenolates. So these compounds which are connected have, of course, their structures were solved by using X-ray crystallography. So the main feature is to show you that the cobalt is has a distorted octahedral geometry, and the yttrium has, as you can see here, there are several coordination sites, and these are filled up by oxygens, and you have 9 coordination around yttrium. We have a candidate that would behave like a single molecule magnet. And how do you know that these molecules have this behavior? So one of the ways one can do this is by doing magnetic measurements, but utilizing AC measurements, AC magnetic measurements. So in the AC magnetic measurements, for example, in this plot that I'm showing you, you have this in the plot of chi double prime m versus nu, or chi double prime m versus temperature, you have this maxima that are generated, which depend upon the frequency of the measurement. And the reason this happens is because if you had a normal paramagnetic substance, and you were to vary the frequency of the AC field quite rapidly also, you would not find any difference, because a simple paramagnetic substance can adjust to this variation without any difficulty. But if you have a magnet that is getting magnetized, then there is a lag time during this process, and that is what you pick up by this measurement, and that tells you that the system is magnetized, and therefore the speed of the frequency at which you vary the field has a direct contribution in terms of what you are seeing. So with this sort of a knowledge that just one particular ion, in our case the cobalt 2 itself, can contribute to magnetism, we were looking at single ion magnets based on lanthanide ions. So our aim was to prepare compound that had specifically a lanthanide in a particular geometry, and the geometry we're looking at was pentagonal bipyramid geometry. And so we wanted to fix lanthanide in this geometry. And so we had to design a ligand which would yield such a geometry. So our ligand, therefore, if you can just see the synthesis, starts off with this multifunctional sort of approach, where your final ligand has several nitrogens and has also this oxygens that are present over here, with the possibility that in fact the oxygen can be in a ketoenol tautomerism with the adjacent nitrogen over here. So we anticipated that here you have a large enough pocket that can accommodate the lanthanide ion, and in fact that would have the lanthanide ion in the plane of this pocket, and perhaps you could have the axial sites that would be free for other coordination. And in fact, this works like this. So we have this pocket which is interacting with the lanthanide, and you have the axial sites over here occupied by the chlorides. And this compound was studied on its own, as well as by dilution with diamagnetic host, and studied. And both of these studies gave very good results in terms of their single molecule magnet property. So here is just to show you that this geometry is nearly perfectly pentagonal bipyramid, with the axial sites having the chlorides and the equatorial pentagonal plane occupied by the various nitrogen and the oxide ligands that the ligand provides. And this can in fact be duplicated with other lanthanide ions, like for example the terbium over here. And you can see the very nice plots of the AC susceptibility versus temperature, and similar things you can also see with the chi double prime versus the new plots. Now, one other small detail in this type of studies is there is always this question: are these properties that you are generating, is it a result of intermolecular interactions, or is it just because of the molecule? So one of the ways of resolving this is by actually diluting it in a diamagnetic host, which is completely isostructural to the parent that you're looking at. So we prepared an yttrium complex, which is also pentagonal bipyramid, co-crystallized it with the dysprosium in a ratio of 10:1. So you have a diamagnetic host which is hosting the dysprosium guest, and therefore the statistical probability that two dysprosium molecules will exist together is minimized, and you repeat the study. And when you repeat the study, if it gets very similar properties, then you know that the molecule property that you're seeing is completely from the molecule and not as a result of intermolecular interactions. And therefore, as a result of these studies, when we get this and we analyze this, we found that the energy barrier is about 70K, which is reasonable but not very high. So we thought, is it possible for us to increase the crystal field strength in the axial site? And we did this by putting a phosphine oxide, a tricyclohexyl phosphine oxide, and one chloride is still retained. And you can see really a dramatic increase in the energy barrier, which goes nearly threefold from 70 to 204. And in fact, all other properties are also really matching with this anticipation. So this kind of study, which is the design-based study, therefore allows us to test this hypothesis. We knew that increasing the axial crystal field would have a beneficial effect in this property, because we knew that this axial increasing the axial crystal field would actually increase the spacing between the MJ states of the lanthanide ions, between the ground and the excited state, and that should result in improved properties. So this is one of the benefits of doing the studies in a systematic manner, so that you analyze the result, come to a hypothesis, and that hypothesis can be further verified by a new experiment. So this was a result that was published very recently. Similarly, we had, having known that this pentagonal bipyramid type of geometries are quite important in these kinds of studies, we started to see if there are other ways we can generate them. And this is again two further papers that have just been published from our group. So one of them deals with a sterically hindered acetyl astronate ligand. So you can see that there is a mesetyl group over here on either side. So normally you have this methyl acetyl astronate, which is the methyl group. This has been replaced with a mesetyl group on either side. And when we interact this with the lanthanide salt, we have distorted 7-coordinate geometry arising at this lanthanide, the 7th coordination being taken up by the DMF molecule, which also, like in the previous examples, this compound shows very good behavior. Similarly, when we use a multifunctional ligand, such as what I've shown over here, and again, by design, which probably is not so obvious, but maybe I'll just allude to it, you have this phenolate, which can bridge two different metal centers, and then you have the possibility of either a keto or an enol tautomerism, which would depend upon the base that we use in the reaction medium. So if you minimize the base, you can have the keto group interacting, and that's what happens over here with the H, for example, not getting deprotonated, and we generate a dinuclear complex, both of the dysprosium being in pentagonal bipyramidal geometries. And both these compounds show very good SMM properties, as I had shown earlier. So I think basically what I wanted to show you in this very short talk was where is this field? This molecule, single molecule magnets was an area that was started with purely academic interest, where molecules which could behave like conventional magnets was discovered, and several approaches of preparing them are now becoming more and more apparent about what are the factors that are needed to be modulated to give you better and better magnets. And once we know that, I think we are in a situation to harness the properties and see if we can get them into some applications. To summarize, therefore, what I've shown you is a variety of synthetic strategies for 3D, 3D, 4F, and 4F complexes. Some of them are based on what could be called as serendipitous methods, but many of them are based completely on design. And the trend is currently to move away from the serendipitous-based methods to move towards rational design. One of the topics, I mean, I did not really dwell much on this, is it is becoming more important that it is not just enough to have a large ground state spin, but it is very important to have significant magnetic anisotropy that can be brought in either structurally or because of the inherent nature of the metal ion that is involved, and that contributes to the overall property. And finally, mononuclear single molecule magnets or the single ion magnets seem to be holding a lot of promise, at least in terms of understanding this phenomenon, because the number of variables get reduced. You have just one paramagnetic metal ion, and what you're really doing is change the ligand environment around it, so it allows you to understand what's happening really well. So with that, Sairam again, and thank you very much for this opportunity.
I'm extremely thankful to Professor V. Chandrasekhar for his enlightening presentation on the lanthanide complexes as single ion magnets. I'm sure all the young researchers will start working on this exciting field. He has given very valuable inputs. I, being an organic chemist, I'm also excited as I saw many of the organic molecules being used as ligands for this single molecule magnets. I'm very thankful, sir. In spite of your very busy schedule, you have made it possible to address the audience. I'm extremely thankful for your presence today. Sairam.
Saira.